Hi, so before we begin this lecture, which will be on absolute dependent motion of two particles, I just want to make sure that you have a chance to look at this lecture slides that I'm going to be uploading along with these notes. That way you can follow along anytime I point to one of the slides and discuss. The slides will have a slide number at the top left corner, so that way you can easily reference the slide number that I am talking about. So let's begin. So we started talking about this topic about absolute dependent motion of two particles. So if you're looking at the slideshow, this is slide 3. And I mentioned that this is composed of two parts, where the positions that we measure are absolute, but also the bodies that are connected, that are interconnected, have dependent motion, which means we cannot move one body without moving the other. And these problems are typically composed of pulleys and gears that are interconnected by inextensible, in other words, these are rigid, cords, cables, belts, or ropes. Now we do have a specific solving approach that we can follow, okay, and that will be highlighted in the problem that we solve together. But let me just go through each of those steps that we have here in the slide. So we have to first define position coordinates from a fixed datum line along the path of each particle. Different datum lines can be used for each particle. So let me just go ahead and highlight these steps here for the approach. So we have to define position from a fixed datum line. I'm going to say line or lines because sometimes we may have multiple reference locations, and these need to be along the path of each particle. Okay. Each particle. Okay. Now, secondly, we need to then relate the position coordinates to the chord length. Those segments of chord do not change. As we said, these are inextensible in length during and throughout the motion. In other words, those can be left out. So let's go ahead and say we will form a relationship between the position coordinates. That's the primary thing, okay? And anything that does not change, we can leave out. Leave out, in other words, ignore segments of chord that do not change in length. Okay. Thirdly, okay, if we have a system that contains more than one chord, we're going to relate the position of a point on one chord to a point on another chord. This way we'll be able to relate the two equations together, but we will need to rewrite separate equations for each chord. So write separate equations for each chord. Okay, but we'll need some specific relationship that we can relate between those two these separate equations. And then lastly, our fourth step is rather straightforward. We can differentiate the position coordinate equations or equation to form the velocity and acceleration relationships. And we must be careful to maintain the signs that we have in our equations. Differentiate position equations to find velocity and acceleration relationships. Okay. All right, so let me just highlight here. This is along the path of the particle. We're going to define position. Second one, we're going to form a relationship between the coordinates, and we're going to ignore segments that do not change in length. We'll write separate equations for each chord, and then finally we'll differentiate the position equations we have. Okay, so if we move on to the next slide, which is going to be the example we'll discuss, and we'll apply these 4 steps in our approach. Okay, so what we are given here in the figure is the chord at A is being pulled down with a speed of 3 meters per second. Okay, now what we're interested in finding is the speed of block D. Okay, so very simply what we have here is a first pulley B that is fixed here at a top surface alongside another pulley, pulley C, that is fixed to that same top surface. Okay, and then we have a cord that is running throughout pulleys B and C, and are being connected with a third pulley down at the bottom, which is pulley A. Or, I'm sorry, we don't have a name for this pulley. Okay, so if we can draw this to scale as best as possible. Okay, we have this pulley that's wrapped around this, or the cord that's wrapped around this pulley. This is our end A that we're pulling down at a speed of 3 meters per second. Okay, so that's some given information. And finally, we have our block D. Okay, so one thing we need to first look at in this problem, okay, is just to recognize, before we even start the approach, is to recognize that this is one continuous chord throughout the system. So as a little bit of pre-work, we can at least see that for step 3, we'll just have to deal with a single equation. Okay, so what we're given in this problem, right, is the velocity at A. I'll write it again here. What we need to find, okay, is the speed of block D. So V at block D. And I wrote a note here in the slide, on slide 4, that there is only one chord involved, as I mentioned. So we only need one equation. Define position coordinates for block D and cable length. So this is a little bit of pre-work that we can focus on how we're going to tackle this problem. We're going to write the position relation and then differentiate it to define the 2 velocities. So let's go ahead and get through and solving the problem. So as our first step, and we can follow along with the solution that we have on step 5, the steps are outlined so that we can follow along how we would apply this approach. So we have to define a position from a fixed datum line. So first, where are our datum lines? Well, we can recognize that B and C here are at fixed positions, these pulleys, with respect to this upper surface, whereas this pulley and this block are not fixed and will have some motion. Therefore, we can define a first datum line up here. All right. And then from here, we can define the positions of coordinates A and coordinates B. By the way, notice how this pulley, we don't have a designation specifically because there is no relative motion between the pulley and this block. So we can think of this as one continuous object that is going to be moving. So if we're going to just keep track of the motion for this, keep the same color, we can track the motion of pulley D in this way. I extend a line from this point, and we can keep track of the position coordinate, let's see here, at A. Okay, so this will be SD, position of D, and position of A. Okay, and in this case I've chosen for the direction of my position to be in this downward direction. And notice how this is along the path of each particle. So this is along, this vertical motion is along the path. Okay. Now the next step is to form a relationship. So we can go and jump to slide 6. We're starting step 2. And we're going to write a position equation for the chord. Okay. Now, here when we start the solution, okay, now I can recognize that because we have one continuous chord, then I can say that the entire length of that chord is some distance LT. Okay, so this is the total length of chord. All right. Now in step 2, there's a couple of parts that we need to address. Okay, first we can recognize the parts of this formula, parts of this chord length that we can leave out, and therefore the chord length does not change throughout those segments. And that typically occurs here when we have the chord wrapped around and in contact with a pulley. So we see here this distance, and finally this distance. Okay, so these segments can be ignored, and so because the length will not change. So therefore we can define that the total length of the chord here will be some distance SA plus this distance, which is actually, with respect to our datum, SD, this distance, which is also SD, and finally this distance. So that's what gives us the equation that we have in slide 6 to be SA SD, or 3 times SD. Okay. Okay. So this forms the relationship that we have between the position coordinates SA and SD. And now we can move on to step 3. And as we had already concluded at the beginning when we looked at this problem, this is one single length. All right, so then we have just one equation to work with. And finally, that's step 3. We can begin step 4. So in slide 6 is listed as step 3, but we have step 4 here where we're going to differentiate this position equation to get velocity first, and then we'll get the acceleration equation. So if this is some constant length for the total length of the chord, so when I differentiate this with respect to time, this entire equation, I end up getting 0 equal to, this is dSA dt plus d3sd dt. Or very simply here, dSA dt is just velocity at A. ds d dt 3 times is 3 velocity of d. The sum of these two equal to 0, or simply we get that the velocity at A is equal to negative 3 velocity d. Now you can just maintain this equation as is, VA plus 3VD is equal to 0, or simply show the relationship for VA. Okay. Now actually we don't even need to differentiate this a second time to get acceleration, because if we look at what we're asked in the problem, we're asked to solve for VD. So notice how we're given the velocity of VA, and we can directly then now solve for the velocity of VD. I'm going to say, if I say velocity of VA is equal to 3 meters per second, that is equal to negative 3 times VD. Now if we solve for VD, this is just negative 3 divided by both sides, and I get negative 1.0 meters per second. And that's the answer. Okay, so notice the negative here is because our positive direction, the way we measured this coordinate was positive down, we got a negative 1.0 meters per second. And therefore, here, the velocity of d of the block is going to be moving in the opposite direction, which is going to be upward. That's what we have in the solution on slide 6 as 1 meter per second upward. Okay. Now then, our discussion now leads to talking about a small topic that we're going to really investigate more in chapter 13, but it's this idea of relative motion between two particles. So the idea here is that we have a first fixed reference frame that we've been working with to define either our position in rectangular coordinates, normal and tangential, or the last one was polar or cylindrical coordinates. Okay, but relative motion between two particles involves the situation where we need to identify a second or more reference frame in order for us to capture the entire motion. So in these problems we encounter, so this is going to be relative motion of two particles. So in these problems, okay, there's two solving approaches, okay. And we need to just select which one would work best for this particular problem. And you most likely have seen this idea in already in your statics course, where a first approach, okay, would be to say, okay, if I have a first particle with respect to some inertial reference point, and then this is my particle A. Okay, we've seen the case where we can draw a position vector here to reference the position of particle A. So this would be R of A. Okay. Now, on a just to give this a little bit of context, we can define our rectangular or Cartesian reference frame, xy. However, if we have a second particle that we're dealing with, let's say this is particle B over here, then we can similarly draw a position vector to locate B with respect to our inertial reference point, as such. But as we learned in statics, we can relate the position here between two particles. Specifically, particle B, we can relate its position if we know the position of particle A. And so we can say that the position of B with respect to A, so here notice the notation b/a. So b with respect to a is given as such. And all we have simply is a vector addition of these vectors. So in other words, for relative position, and I should really call this first approach as our vector approach. Okay, relative position becomes, so by vector addition, if I add up vectors RA and RB with respect to A, then that gets me to the same location as vector RB. Okay, and if we differentiate this with respect to time, then we can form an equation that relates the motion, the relative motion of these two particles. So differentiate with respect to time, this becomes VA, velocity of B with respect to A, equal to the velocity of B. Okay. Now the big takeaway here is to highlight the fact that VA and VB are absolute absolute positions, absolute velocities, and therefore, sorry about that, and therefore these RA and RB are absolute positions. We call them absolute because they are referenced with respect to our inertial point. Now these relative position, RB with respect to A is a relative position. So then that makes VB with respect to A as a relative velocity. And therefore RB with respect to A relative position. Okay, so this is one approach where we can use vector addition to come up with how we can describe the motion of particle B in cases when we don't have this vector RB, but instead we have this relative position, RB with respect to A. Now the second approach is to use geometry. So we can do this graphically. All right, now whenever this does occur, we will have to rely on the law of sines or the law of cosines to help us resolve, in order for us to resolve the necessary lengths of these vectors that we need. Okay, so let's take a look here on slide, so I was just on slide 7, but if we look at slide 8, we see here as a way for our own reference what the law of sines and law of cosines enables us to calculate. So just for reference, the little a, little b, little c are distances of the sides of a triangle. So you can think of those sides of a triangle as what we have here on paper, the vectors, whether it's position or velocity. And then capital A, B, and C are the internal angles. So it may be that we need to draw these vectors in order for us to then resolve what the relative positions and relative velocities would be. Okay, so how we would find these angles is we can use geometry to find the angles based on what we know about the vector. So using its unit directions and finding the direction of the vectors in space. So very simply there we have in the slide 8 what the law of sines and law of cosines is with relation to those side lengths and internal angles. Now you won't need to memorize this, but it will be provided, or you should have a quick reference to it whenever you're solving these problems. But you're not restricted to solving one problem one way or the other. There will be opportunities where one approach may make more sense than solving it the other way. So here in this example, on slide 9, okay, we have the relative motion between two airplanes. One traveling at 650 kilometers per hour, that's plane A, and the other one traveling at a velocity of 800 kilometers per hour. So this is our second example. Let me just highlight what we're given. Okay, so VA is equal to 650 kilometers per hour. Velocity of plane B is 800 kilometers per hour. So we're observing this to be a relative motion problem, okay, and we're asked to find what the velocity of plane B is with respect to plane A. And notice we have some inertial reference point there in the figure that we can identify. So moving on to slide 10, okay, we're going to try to solve this using both approaches that we just discussed. So the first one being the vector method, okay. So notice how we understand from the figure that the velocity of 650 meters per kilometers per hour is given as a direction that's traveling really, so velocity of vector VA is positive 650 in the I hat direction. This is kilometers per hour. And the velocity of plane B here is traveling at an angle of 60 degrees relative to the horizontal axis. So that translates to a negative I component and a negative J component. So velocity vector VB is given by negative 800. Okay, and that will be cosine of 60 degrees. This is in the I hat direction, and negative 800 sine 60 degrees in the J hat direction. Okay, so we have our vectors, velocity vectors VA, VB. So what we can do is, when we solve this problem, we can take our equation that we have, VA plus velocity of B with respect to A equal to VB, okay, and solve it for velocity of B with respect to A to be the difference between VB minus VA. And so at this point it just becomes a vector addition problem, or in this case a subtraction. So we're subtracting the velocity of VB and velocity of VA. And there you can see in the problem, when we do this, we end up with negative 1050 in the I hat direction minus 692.8 in the J hat direction. Okay, now what I didn't make a point to point out here, and what we're trying to find is the magnitude. Okay, so this is trying to find the magnitude, the speed. I should write speed. So to find velocity of B with respect to A, we have to find the magnitude of the vector, which requires squaring the I component, squaring the J component, adding them, and taking the square root. And there we get 1258 kilometers per hour. Okay. We're not asked to find the direction, but there you can see that we do have the angle theta that is provided based on taking the y component divided by the x component and taking the inverse tangent. So notice theta here is calculated as being the inverse tangent of my VB with respect to a y component over velocity of VB with respect to a x component. That is 33.4 degrees. Now, as a secondary approach, there we have in the slide 11 how we would solve this graphically is we would find the internal angle. So if I just look at the slide here, I see I have an internal angle of 120 degrees that is separating the velocity vector VA and VB. Notice I had to superimpose the and move the velocity b vector so that its end is touching the starting point of velocity vector VA, and which then allowed us to identify where velocity b with respect to A is located. So you can solve this problem even within this graphical method using either the law of cosines or the law of sines. So here we have two sides of our triangle that are given, which are the speeds, and then we have one internal angle. So, and we're interested in finding the length, in other words, the magnitude of VB with respect to A. So using the law of sines, we can find that directly, or law of cosines. Okay, but the law of sines allows us to give us the answer that we want. That's the law of cosines, versus the law of sines gives us the angle in which the direction of that vector. Okay. And just to sum up, okay, we will have another example that you'll be able to complete in the TA recitation. But as to prepare you for what you were going to see in class on Monday, I want you to just review Newton's second law of motion, which is slides 12 and 13. So slide 12 here just shows us the classic F is equal to ma equation that we're going to apply now moving forward. And we just need to get an understanding of what mass is as a property of the rigid bodies that we're going to analyze. Okay, and going on to slide 13, okay, some other concepts that we want to review when we go into the next lecture are some of the concepts that we've already discussed, which were inertial reference point, and some, as well as some topics that we've covered in statics, such as free body diagrams. Okay, because we're going to have to draw a free body diagram for each of the problems that we analyze. But a new concept, if you will be the idea of adding the additional reference frames, and in particular just defining a inertial reference frame for our problems. Now, a kinetic diagram is a little bit of a new concept, but that represents any inertial forces on mass center. These inertial forces are essentially the accelerations that are acting on a mass center. So we'll get into how those look. They're actually rather simple. They don't require as many forces or to draw as many forces as a free body diagram will require. But it allows us to connect then the pieces when we do apply the Newton's second law to connect the free body diagram, which are the external forces, to the kinetic diagram, which are the inertial forces acting on the mass center of a rigid body. So please review those last two slides, 12 and 13, and we will pick up class again on Monday. Okay, hope everyone has a good weekend, and we'll see you on Monday.